Hello, and welcome to Ask John. I'm John Reuscher, and this is a show that was conceived with the idea that people would come on my show and ask me questions. I'm a financial advisor, and anytime you have a financial question, you're welcome to call me. In the first couple of episodes of this show, I had people on that asked me financial questions, and then it turned out I was asking them more questions than were being asked of me, and I realized that I enjoyed asking the questions and didn't necessarily need to be on a financial topic. So today, we have another exception. So almost all of my episodes are exceptions to the rule of Ask John. Today I have as my guest Dr. Andrew Gunther, and we are going to talk about climate change. How about that? Are we ready for that? A topic that's in the news and on our minds all the time. Dr. Gunther, tell me a little bit about yourself.
Well, I'm a professional environmental scientist. I've worked at the intersection of science and policy for about 35 years, helping mainly state and local governments develop scientific programs that help them answer questions. I've done a lot of work on water pollution in San Francisco Bay. I was involved in the Exxon Valdez oil spill restoration program. And then the last 10 years, I've spent a lot of time helping government agencies in the Bay Area prepare for our changing climate.
So you are currently retired.
I am semi-retired.
You're semi-retired.
Seems to be a little bit more on the retired than the semi.
You're sort of on the circuit, aren't you?
I spend a lot of time trying to educate people about climate science.
Yeah,
Absolutely.
I've heard two talks that you gave, which are just so compelling, and I heard you talk at one organization, and it was such a wonderful talk that I asked you to come talk to my Rotary Club, and you did, and you did not disappoint.
You're my Marin County agent.
I am. So this is your third gig in Marin County. So you're retired. But what you're doing is you're addressing community groups. Is that
absolutely all without charge or anything? My goal is to get us.
Would I call this a hobby? And by the way, can I?
It is more of a calling than
it's
a
a
hobby.
calling. Yes, I understand that.
I have two children, and I see the world changing very, very dramatically. And I want us to stop arguing about whether it's happening, and instead argue about what we can do about it.
I am all for that. I'm all for that, and I think anyone should be, even people who may have skepticals or even deniers. I think we should all be in the camp that says it doesn't matter. Let's solve the problems that we have in the world, and we have a lot of problems. So I'm in your camp there.
Okay.
So this is not a hobby. This is a calling, and so here you are. What do you want to say?
Well, I thought that I could just do a little summary presentation of some of the things that I talk about, and then I'd be happy to answer your questions. You can wave me down and interrupt me if you like.
Okay, so we have a presentation all set up here, and I think it's set up to show on our monitor. Can we get that started?
Sure, yeah.
Okay.
So when I talk about climate change, I like to use three questions to frame it, which is, must we change? Can we change? And will we change? And to understand why we must change, we need to understand that climate science is actually very old. The first guy who really got this going was Joseph Fourier. And he was a contemporary of Thomas Jefferson's. And he marched with Napoleon, and he was a physicist studying heat. And it was Fourier who realized and postulated that there must be a layer of gases in the atmosphere that act as a blanket, keeping the Earth warmer than it otherwise would be. And that turns out now that Fourier was absolutely right, and this is a principle of physics that's known as the greenhouse effect. And I can show here with the diagram that the Earth gets almost all of its energy from the sun. Most of the sun's rays pass through the atmosphere, striking the planet and warming it up. And just like anything else that warms up, a log in the fireplace or a frying pan on the stove, the Earth begins to radiate heat in the form of infrared radiation, and most of that radiation escapes into outer space. But because there are these heat-trapping gases in the atmosphere, carbon dioxide being a very important one, they absorb some of that outgoing radiation and radiate it back down to the surface of the Earth.
And historically, I'm assuming this is a good thing.
Yes.
Otherwise, we lose all our heat. And
that's right. The Earth would be
yeah.
much, much colder
Yeah,
without this
yeah.
effect. Exactly.
Okay.
That's why the Earth has the temperature that it does. Mars has a very thin atmosphere, very weak greenhouse effect. It's a very cold
Very cold,
place.
okay.
Venus has a very thick atmosphere, very powerful greenhouse effect, and has a surface temperature close to that of molten lead. And it's not just because of the relative positions of the planets compared to the Sun, because Mercury, which of course is the closest planet to the Sun, has a very thin atmosphere, very weak greenhouse effect, and has an average
cold.
surface temperature below that of
Interesting.
Venus.
Yeah.
Now, what's happened over the last 250, 300 years is that humans have been adding prodigious amounts of these heat-trapping gases to the atmosphere, mainly by burning coal, oil, and natural gas, and by chopping down forests. And that's had the effect of thickening this layer of heat-trapping gases. So now, energy that used to escape into outer space is being captured by these gases in the atmosphere and radiated back down to the surface. And it's that extra energy that's
the gases
forcing
you're
our
talking
climate
about,
to change.
We're talking about CO2.
CO2 is the main
there
one that we're
something else?
adding, also methane, and there are several others.
And is methane and others the culprit that CO2 is?
Yes, but the reason
But
that
not
we
to-
focus mainly on carbon dioxide is because it stays in the atmosphere for a long, long time. And all the time it's in the atmosphere, it's absorbing heat that would otherwise have escaped to outer space.
And is it easier to do something about CO2 than it is methane or the other gases? Do we have more control over it?
No, it's probably a little easier to control methane release. Well, for the releases that come from our activities. Methane also has natural sources. And one of the challenges we're going to face in the future is as the planet heats up.
Of course, CO2 has natural sources
That's true.
as well.
Yes.
Probably, obviously.
Yes.
Yeah.
Uh-huh. And so Fourier figured this out, in the 1820s, and in 1859, before the U.S. Civil War, Irish physicist John Tyndall demonstrated in the laboratory that, in fact, carbon dioxide can absorb heat. So this is the chemical mechanism underlying Fourier's hypothesis. And in 1896, Swedish chemist Svante Arrhenius published what in essence is the theory of global warming. And he actually calculated with just a piece of paper and a pencil what the temperature for the Earth would be if there was twice as much carbon dioxide in the atmosphere.
Huh.
And he got very close to the answer we get today. And that just shows
Now,
how
did he
fundamental
get close, did he get close to what we're projecting today, or is he close to what actually occurred today?
Well, he is. If we ask the same question today,
Yeah.
if there
We
was
get the
twice
same
as much
answer.
carbon, we get very
Yeah.
close to the same
So
answer.
the problem with any theory is being able to prove it, and you have to have experience to prove it.
Right.
So,
and
yeah.
we, in fact, since we have started burning large amounts of fossil fuels, we are, in fact, conducting an experiment. Unfortunately,
Right.
we're in the experimental apparatus.
Yeah, and the measurement is the most difficult part of that experiment.
Well, I mean, we've learned how to measure carbon dioxide,
Yeah.
and it's very clear carbon dioxide is rising, and it's very clear that the temperature of the planet is rising with it.
Okay.
Yeah.
It's clear to everyone?
It's certainly clear to science.
So
So scientists,
All right,
the reason
I
I
heard
like
you
to
say-
talk
I heard
about
you say
this.
this. Okay, so
is-
let's talk about this.
Okay, sure.
It's clear to science.
Uh-huh.
So I thought scientists were skeptics by nature.
Indeed they are. The oldest scientific society in the world is the Royal Society of London, founded in 1662, and their motto is don't take anybody's word for it.
I remember you saying that, and I remember you talking about scientists
Yes.
are the greatest skeptics.
Absolutely.
And-
Objective skepticism is the
Yeah.
heart of the scientific
And
process.
I'm not sure that you're the one that said this, but what is it? We're saying that 94% of scientists agree that this is a problem, and
There have been six different
Yeah.
surveys conducted, and the numbers range from 91 to 99%.
Can you be really specific though about what was the question that was asked? Who?
Well, I would have to go back and consult those surveys.
Yeah.
I'm not.
I mean, would you
exactly
be able to
sure.
do that?
But Well, sure. I mean, this point has been analyzed and debated over and over again.
Right.
Yeah, absolutely.
Right.
And if I can go back just a minute to
how many
Arrhenius.
scientists are there in the country or the world?
Well, I don't know.
I would.
When I go to the American Geophysical Union meetings,
million?
there's 40,000 there.
Yeah.
It depends what field of science you're talking about. There's a lot, and
So when you ask this question, you're doing a survey, and you're surveying a whole number of people, and you're only being able to tally the people who answered. So you
sure, but that's true with any survey. I mean, you have sampling error
and
that you
there's sort of a
address.
Self-selection there. And I would imagine, I don't know, I don't know, but I imagine that if someone thought it was a concern, they'd be more likely to respond. If someone didn't think it was a concern, they would just not respond to the survey.
Well, there's that kind of sampling bias in any survey, I guess. But the point here is that because Arrhenius was able to make these calculations with just a piece of paper and a pencil and the knowledge of physics in the 1890s, and his projections have been basically proven out because the basic physics that we're talking about here is really, really straightforward and was understood in the 19th century. The finer points about what the future temperature of Nevada will be compared to Sausalito, those are actually much harder questions to answer.
Yeah.
But the basic
this
idea.
Whole question about what is an average temperature? Well, what's an average temperature today? When it started off at 40 degrees this morning, and this afternoon it's 82, and what's the average temperature today? That's got to be.
Well, but remember the average temperature.
I'm trying to imagine how a scientist could even come to a point where they could say with specificity what the average temperature is over a year.
Well, but recognize the larger area of space that you average over, and the larger amount of time you average over.
Yeah.
You're talking about the weather. The difference between the temperature in the morning and the afternoon, you're talking about the weather.
Exactly.
Climate is the average weather.
Right.
And when climate scientists talk about the average weather of the planet, they're looking at 30 years of data for the whole planet and to average that together.
And how did they measure the whole planet? It's a big planet.
It's a big planet. In fact,
we have these tiny little receptors that are making the temperature readings, and they're placed in. How much of the planet? What percentage of the planet is covered with those?
The first global average temperature that we have as measurements. The data sets we have usually go back to around 1885 as the first time where we had enough ships around the planet and we could generate an average temperature. But those estimates of the average temperature of the Earth actually have wider error bars on them than later when we have many, many more sensors to measure. Yeah. And then scientists use what are called proxies. And what you can do with a proxy is, if you understand how it varies with temperature when we have our instrumental record, but that proxy measurement goes further back in time, you can use that to estimate past temperatures.
And ice core.
Well, there you go. That's right, exactly.
And I remember you talking about extracting an ice core that went back how far?
Yes, it went back 800,000 years.
800,000 years.
Yeah. And
so that's something that was happening.
I can even show that information here if you'd like.
I'm trying to get my head around this. Something that happened, a condition that existed 800,000 years ago, is being interpreted to tell us what's going on right now in this, in a 20 or 30
well,
or
what it allows
period.
you to do, when you look over 800,000 years, what you see is that the concentration.
They're going to look at a correlation, but aren't you?
Right. Well, not only does carbon dioxide correlate with temperature over that 800,000 year period, which it didn't have to be so, right? So that core is like an independent test of our understanding of what drives climate. And then when you look at that record, you see carbon dioxide has never been, in that 800,000 years, higher than about 290 parts per million until right now. And right now, carbon dioxide concentrations are at 405 parts per million, higher than they've been.
405 parts per million.
Yeah, so that's higher than it's been in actually until the last time Earth had carbon dioxide concentrations of this magnitude was about 3 million years ago, and there were no people.
So is that necessarily a bad thing, having higher levels of CO2, which actually grows plants? That's a good thing, isn't it?
Well, it does, but it also captures heat. So that is generating a change in our climate, and that's going to
is there any possibility
generate extraordinary stresses on our society.
Is there any possibility that the planet can adjust naturally to a new condition?
Oh, sure. But remember,
Does the planet do that?
The planet does it all the time. But it does it.
Beautiful meadows where forests burn down.
It does it on the scale of thousands and thousands of years, right?
I'm thinking like what happened with like years and years ago. Yosemite, they had this horrible fire, and it was a tragedy. And a year later, we had this beautiful meadow.
Well, but that's the natural process of succession. So one of the things you can do with the data is you can say, so let's look at what the temperature has been during the time that human civilization evolved. So that's about 10,000 years ago was the first cities. Right. And so when you take this ice core data and you just look at the 10,000 years, you see that temperatures went up for over about 4,000 years. They went up a degree Fahrenheit, and then they went down a degree Fahrenheit for the next 4,000 or 5,000 years. Except for the very end of this time record, when in the last 200 years, the temperature has gone up 2 degrees Fahrenheit. Okay. So, and what I like to say, I don't like to say it, but I think it's true, is that our climate, the climate that we had, is gone. We now have a new climate where temperature is rising very fast, and that is going to result in changes all throughout the planet. I think I heard you
say at one point that it's already too late.
It's already too late to prevent the temperature from changing, but the world we get is still going to be the world that we choose. And if we choose to reduce our carbon emissions, and if we choose later in this century to try and extract carbon from the atmosphere.
Did I totally derail you? You had this presentation.
No, you're asking me questions.
Okay, I'm enjoying this.
It's fine. We can do it. My wife can't believe how much I like talking about this. So,
I like talking about it too.
We have, yes, and because carbon dioxide stays in the atmosphere, and this is a really, really important point, as people hear the news and hear scientists talk on the news, and the scientists talk that we've already committed ourselves to change because the carbon dioxide that we've put in the atmosphere stays there for hundreds to thousands of years. So unless we extract it from the atmosphere, all the time it's there, it's absorbing heat. So it's as though we've wrapped ourselves in a blanket we can't take off, and that's why we know change is coming.
You just said we could take it off by absorbing it.
So. Well, sure. I mean, we don't yet have the that's a lot of technology that we're
I don't like it when you say you can't. We were just saying that a while ago. You can't solve the problem by planting trees.
But what we can do,
we can.
Here's the analogy.
Solve part of the problem by planting trees.
Here's the analogy I like to use. Everyone's had the experience, I think, of lighting a fire in a fireplace and realizing the damper is not open. Okay, and then you light a fire and you're doing something. You suddenly realize the room is filled with smoke. Oh my God, the damper is not open. So you open the damper, then you throw open all the windows, and the smoke is gone in 10 minutes. Okay, but that's not how carbon dioxide works. It's as though we suddenly realize there's too much carbon dioxide in the room. We open the windows and find out they're all nailed shut after a quarter of an inch of climb. We can't right now. Carbon dioxide will eventually be absorbed in the ocean and absorbed in the plants, but it will take. That's thousands and thousands of years. The planet has no trouble in thousands and thousands of years. The planet is millions of years.
Well, your ice core went back 800,000 years, right?
And in fact, in the Pliocene, about 3 million years ago, carbon dioxide concentrations appeared to be at around this 400 parts per million level, but there was no humans then.
Is it per million or billion?
It's 400 parts per billion.
Billion,
yes.
Per billion. And so, if I'm going to
I'm sorry. It's 400 parts per million.
Is it million?
Yeah, 400 parts per million.
I've heard it both ways, so I don't know.
There's a question I haven't been asked in a while. I'm like, wait a minute.
It's an incomprehensible number. So if you want a greenhouse, I'm not talking about the greenhouse effect. I mean, if you want to grow plants in a greenhouse, you pump up the CO2.
You do.
And how high do you pump that up?
Well, it depends on the plant. Not all plants respond. Unfortunately, ragweed responds really well to increased carbon dioxide. But remember, plants don't just need carbon dioxide. They also need water.
Right.
And they need other nutrients in the soil.
And they need the nutrients in the soil.
And they need the sunlight.
And if they have more CO2, then they need less of the other elements. Is that right? Is that right or no?
No, that's not necessarily right. If
It's
they
not right.
think about it this way, if they have everything else they need and you give them more CO2, they can grow faster.
Right.
Right? But if you give them more CO2 but they're out of water, suddenly that
Right.
becomes the limiting factor.
Yeah, of course. Yeah. Well, so it's fair to say that you get more production with the same elements if you add more CO2. You have the same amount of water.
Yes,
the
and
same amount
again,
of
different
nutrients.
plants respond differently. But that in general is true.
Yeah.
Uh-huh.
Yeah, and so those plants are absorbing the CO2, and so the greenhouse farmer has to pump more CO2 into it.
Mm-hmm. So
Okay.
I mean, this
All right.
is the natural carbon cycle. One interesting way to think about it is that there's only a set amount of carbon.
That's something that maybe happens over hours or days, and not centuries like you're talking about.
In a greenhouse, you mean?
In a greenhouse, it's happening.
In days to weeks. Yes.
Yeah. Mm-hmm. So if we want to try to solve our own problems this way on the planet, okay, I heard what you said a while ago. We can't just plant trees. No, you didn't say you can't. I said you can't just plant trees. So you can plant trees, and you can plant there are other plants that absorb.
Even more importantly,
So
you can stop chopping trees down that are already there.
Yeah. Well, some of the trees we need to chop down so we can manage the forest properly, and that was another topic we had.
But some
let's
of
not go there.
our major forests, you can think of them as the lungs of the planet, pulling carbon dioxide out and releasing oxygen. And the deforestation. When you chop trees down, you clear forests. A lot of that woody material starts to decompose and produce carbon dioxide.
So what if we found the plants that absorb the CO2 the best, most efficiently, quickest, and we planted them all over the earth? How long would it take us to do that? And how long would it have an effect? How long would it take for it to have an effect?
It depends on how fast the plants grow. Do the plants die? One of the great storehouses
if they do,
of
we'll
carbon.
plant another one.
Well, redwood forests.
You know that, right?
Redwood forests are one of the great storehouses of carbon.
Plants do normally.
Yeah. But some plants live for a very long time, like redwood trees.
Yeah.
And they are taking carbon dioxide in, and then the leaf litter and everything, all the soil, carbon accumulates in the soil as well. It's possible for farmers, for example, to adopt practices that pull more carbon into the soil, which turns out makes the soil more fertile over time. And so one of the ideas, you can think about the solutions as slices of a pie, and there's a whole set of solutions that we need to.
Well, this one
move on
solution:
this issue.
plants. Planting more plants that are the most efficient in absorbing CO2.
Yes.
And so I know there's not an answer to this question, but I'm going to ask it anyway. So is that 50%? Is that 10% of the solution? Is that 90%? An infinitesimal amount of solution?
No, the research I've seen suggests that what we call these natural carbon solutions, where we are encouraging our natural ecosystems to pull carbon out of the atmosphere, we're planting trees, afforestation as opposed to deforestation, is somewhere between 15 and 25%.
Significant.
It's an important piece of pie. And you have scientists like down at the Salk Institute in UC San Diego working on genetically modified plants that actually add more, they build fatter roots, you could think about it. They basically create cork in their roots. And so they actually pull more carbon out of the atmosphere. And one idea would be to engineer our crops to have these fat roots so that after when we plow the field, all that carbon stays in the field.
It stays in the earth.
Yes.
Oh.
Right. But not only does it stay in the earth, but it came from the atmosphere and stays in the earth.
So we're containing it, basically.
Yes, exactly.
Yeah.
Right.
Excellent.
Right. There's a set amount of carbon in the planet. The carbon in my nose could have been a dinosaur's toenail 65 million years ago, and it moves. The carbon moves between the ocean and the plants and.
Andy, can I call you Andrew? Andrew?
Yeah.
Andrew?
Andy.
Like Andy? Okay. Yeah. I didn't want to think about the carbon in your nose. Okay. So, what other solutions are there?
So we need to be able to generate electricity without using fossil fuels, and that means using carbon-free electricity includes hydroelectric power, solar power, wind power, nuclear power, or burning fossil fuels, but then extracting the carbon from the exhaust gases before they're released to the atmosphere. And we know how to do these things. The prices of wind and solar in particular have plummeted in the last 25 years.
Why
making
is
it
that?
much more
What has caused the prices to plummet?
Well,
is it
both,
is it
both
economy of scale?
it's kind of the innovation curve that
Yeah.
that we saw cell phones take, and
Right.
but particularly when you can manufacture at scale,
Right.
then you're able to spread your costs out over many more units, and so you can really capture much more of that, that
we've had-
economy of scale.
We've had hydro forever, probably our first
Mm-hmm.
energy source, and wind power seems like it's hugely problematic because I don't know. You hear about birds, and
Well, you know why we hear about that particularly here? Because one of the first wind farms in the United States was sited out at Altamont Pass.
Right.
And not enough attention was given to the fact that Altamont Pass is an important migratory path for raptors in particular.
Yeah.
So their buildings and cats kill many more birds than wind turbines do.
say
and
that again.
Buildings, so
Yeah.
birds running in the buildings,
Ah.
and house cats
Oh.
are a much bigger
The
much
house-
bigger problem for birds
Yeah.
than wind turbines
Yeah.
are. And now we're
Birds
we're-
die of old age too. don't
and
they?
now we're beginning to locate wind turbines offshore, where we can we're making them very large, and they're
Go after
very
different
productive.
kinds of birds, seagulls.
Well, but there are in a lot of these places there are a lot fewer
Yeah.
birds.
Yeah.
The
So placement is huge.
placement is very important.
Yeah,
and
that's huge.
but there's
So-
plenty of places where it's
So
windy.
wind
and we can-
and solar. I think I hear you're saying that solar is improving, being much more efficient than it used to be.
Absolutely.
Yeah.
But of course, when the sun goes down, you don't get much solar power.
Right, and so storage is a big
critical.
deal, and that's improving
right.
as well.
Absolutely. And batteries are on the same technological innovation curve where cost is coming down. And so now suddenly we're beginning to see the electrification of our vehicle fleet,
Yeah.
where you have a car now where the batteries can store 220, 250, 300 miles of driving.
Yeah. And I
and-
noticed you drove over here on battery power.
I did.
You
I
stored
did.
that
I got to
power.
put
You-
my money where my mouth is, right?
You charged that up last night, and you drove over here.
Right, absolutely. And yeah, so I always tell people, if you haven't driven an electric car, go do it, because they have fewer moving parts, there's a lot less maintenance,
Yeah.
and it's very quiet and it's wonderful.
Very comfortable,
But
yeah.
but we're going to have to work really hard. It's one thing to talk about this in the abstract,
Yeah.
but if we're going to make it, eventually we have to
So
draw a
what-
line in the sand and say no
so
more
what-
internal combustion engines.
So what I'm hearing you say, and that's a hard thing. That is a really hard thing to sell, because we have our economy, our industry is just built on internal combustion and in all of that. But and I forgot I was going to make a really interesting point, and I forgot.
Well, I think
So
where
go
you
on.
were going is this idea that the
Oh.
solution to the problem is multiple.
It is.
It's
So
multiple,
those
yeah.
those three things. So we're talking about plants, which pulls the carbon out of the atmosphere, and then we were talking about other sources of energy. So and you put plants at the 10 to 15% range, I think, and then how about well, do we completely solve the problem if we go completely off of the internal combustion engine?
Is that
completely solve the problem?
that's a big slice of the pie, but it's
Yeah.
not the only
So
slice.
how
of the
big
pie.
a pie is how big? a piece
Because
of that
we
pie is
have, well, it depends. So in California now, about half of our carbon emissions come from our vehicles.
that? Yeah.
And so we have to transition. Now,
So
it's
you're getting into
important
this
to
thing is we can, but will we? That's, I think.
Well,
yeah,
and so
yeah.
that's the real.
And
I like to say we must change. We can change, thank goodness.
And the question
but
is,
will we change?
yeah.
And what's interesting to me to see there is how our politics is shifting.
Right.
And in particular, the voice of the young people. Now, you and I, graybeards like us, we're not going to see the worst of this. But the young people who are alive today, people under the age of 20,
Yeah.
when they're our age, the world is going to be very, very different.
I really hope that we're not scaring them unnecessarily. I really hope young people today have just this awful feeling about their future. And what if we're wrong?
Well, I think
What if we're wrong about the problem? What if we're wrong about the problem? What are we doing to our children?
well, we've only created a cleaner world, I guess. That's without emissions, but we're
creating children
not.
with,
but we're not
with
wrong, John.
With issues.
We're not wrong. I mean, we have understood this problem for 150 years.
Some people have.
Well, but
people.
I mean,
I haven't. I don't have the education or the training or the ability.
But the
to understand
scientific
this problem.
community has been. Every president since Lyndon Johnson has been warned of this problem, and we have. And the other thing to
maybe
recognize.
that's the crux of the issue, is that we should stop getting our presidents involved in this. Get the politics out of it.
Well,
solve the problem on our own.
But we need the leadership to make these changes. You know, Amory Levin says the Stone Age didn't end because we ran out of stones. And the fossil fuel age can't end. It can end even though we are not running out of fossil fuels.
In the model, in the economic model that we live in, it has to make economic sense for us to do that.
Indeed, it does.
Or it's going to take a law that our society just won't accept.
But the reason that our leaders should be adopting these policies is because the most expensive thing is to do nothing.
Yeah.
That is, as the temperature rise
Have you noticed that our leaders are more concerned about getting elected than they are about solving any problems?
Well, they are, but if you look now,
I just want to make sure we're talking about reality here.
But this is a real problem, and we are seeing many leaders in the United States, not the Republican Party in the United States, but the Republican Party in the United States is really an exception globally, and we can talk about why that is, but the fact is that more and more young people are recognizing that it is our generation that has to take action to protect them. Yeah. And that is what the science is telling us. Exactly how we do it, I don't know. Well, I think we need to try multiple policies and see what works.
I should have given you advance notice so you could prepare for that main question that I have about the percentage of scientists, and what is the universe of scientists that you could have polled, and then who did you poll, and then who responded?
John, that poll has been
amazing.
Tell me why why is that important to you? Do you think there are scientists who are making arguments that somehow the physics that we understand is incorrect?
No, I think that the problem is it's huge. It's a multivariate issue, and when I hear that science is settled on this, and I know that it is a huge multivariate problem, the alarm bells go off. Science has never settled on anything. Science is not even settled on transmission of electricity. It's just proven every day. It's just proven. It's transmission of electricity.
So you're saying that one day you think that suddenly electrical transmission will stop working? You're saying the science isn't settled?
I'm using a really, really, really bad analogy. I'm saying that theory is that you can generate electricity and transmit it. That's a theory, and we prove that every day.
That's correct.
And we cannot prove climate change. We can have lots of theories about it.
I would argue to you that we have already proven it.
Okay.
That we made predictions. So the Jason Committee of the Department of Defense and the National Academy of Sciences made predictions in the late 1970s. And they said, we are going to see a pattern on this planet where temperatures are going to go up, but they're going to go up faster in the Arctic and subarctic than they will in the temperate regions. And that is exactly what's happened. Okay. Arrhenius predicted that in 1896 the temperatures would go up.
Do you know there are people that are, and I'm not I don't know. I'm just a guy here, and I don't have any knowledge. I just know that there are people that I think are scientists. Well, I know they're scientists that I think that are pretty smart, that would take a different position than you are.
Well, I would encourage you to bring them on and interview them.
I will.
And here's another thing I would ask you to do, which is that
Would you like to talk one of them?
Consider.
I would think it'd be fun to have you have.
Well, I think that we would get down into the weeds.
Fun to be
we'd get down in the weeds so fast your audience would lose interest. But here's an interesting way to look at this: is that if you recall, there was a lot of request that the federal government start regulating carbon during the George W. Bush administration. And they were dragging their heels, and the state of Massachusetts sued them. And the case went to the Supreme Court. And the state of Massachusetts was saying, we know what's happening, and as we add more carbon to the atmosphere, there's going to be more and more of a threat, more and more impacts, and so we must regulate carbon as a threat to public health and safety, which is the rationale for the Clean Air Act. And so they were saying the federal government was violating the Clean Air Act. And there was a debate in front of the Supreme Court, and the Supreme Court decided 7-2 that there must be regulation of carbon because there was no other explanation for what we are seeing on the planet. Okay. This is the point, that there is no other explanation.
Wait a minute. We don't know if there's another explanation.
Tell me why.
I don't have another explanation. You're asking me for one? I don't have one. We just don't know. Don't say there is none, because we just don't know. Tell me you don't know of another explanation.
If I throw this over my shoulder, is it going to land on the ceiling? No, it's not. Okay. Right? So well, you know that. And I'm look, I am always open to someone saying, we've discovered something else.
Nature surprises us in so many ways.
Scientists have been studying this problem since the middle of the 19th century. And there's this entire consistent body of knowledge.
We skipped over one little thing. Well, not one little thing. We skipped over the one thing about, or did we cover forestry change and agricultural practices?
Well, that's the idea of where we can bring carbon into the soils. And in fact, this is another way farmers can get paid for their practices. It would be, we should be encouraging our farmers to farm carbon in addition to the crops.
Okay. Well, we really are out of time. Or we're really very close to it. But is there anything else you want to add?
Well, I really appreciate the skepticism you're bringing to some of these questions. But I would encourage you to recognize the risk that we are taking here. Right now, we have 150 years of science telling us one thing, and every so often there's somebody on the internet saying something else. And we are going to be making investments. We are going to be building new transportation systems. We're going to be building new buildings. We are going to be building new power plants, and we have a chance to make those investments. Use that capital to prepare for the world that's coming. If we only use the past to make our preparations, we're going to be paying serious costs in the future. We can't prevent climate change from happening. The climate change that's coming in the next 20 years has already been decided by the emissions we put in the atmosphere. But if we take action today, 30, 40, 50 years from now, things can be different. And that's what I hope. You know, Rusty Schweikert, the Apollo
one thing
astronaut,
we didn't talk about nuclear. What do you think about nuclear?
We could probably do a whole show about that.
I know we could.
Well, I'll tell you a couple things.
The reason that comes to mind is that the way I want to close this segment is that what we can agree on. All of us can agree. I'm just talking about, everyone can agree that we have problems on this planet, whether they're created by climate change or not. We have problems that we need to address, and one of the things is a cheap source of energy, which nuclear could provide. And perhaps, if we work on solar and so forth, we can lower the cost of our energy. And the other problem we have is that we're having more forest fires. Is that because of climate change and heat? Yeah, suppose so. Could be. I don't know. But I also am pretty sure that it has to do with the way we're managing our forests and letting the detritus fall on the ground, and we're not cleaning it up. And I understand we get a ton per acre per year, a ton of stuff on the ground per year, and that just stacks up because we're not letting it burn off. And when we do get a fire, it's a hot fire, and it burns the tops of the trees. So this is stuff that we need to take care of, whether we buy into climate change or we don't, or whatever, however we think about it. We need to solve those problems. And anyway, if we can get cheap energy through nuclear or through any other source, I'm all on it. And Dr. Gunther, Andy, Andy, I really appreciate you coming on. This has been fun.
Well, I'm glad to be here, John. Thanks so much.
Great. And thank you for joining us. This is one of the, it's a serious topic, but I think it was a good show, and I hope you enjoyed it. And come back. We'll be back. Take care.